last lecture, we have seen direct approach based method which is applied to weakly meshed system. And in today's lecture, we will see Gauss implicit Z matrix method for distribution load flow analysis. So, before going to the Gauss implicit Z bus method, we will just see what we have seen in the last class. So, last class, as I told you, we have applied direct approach based load flow analysis for weakly meshed system. And we have seen that whenever there is weakly meshed, what we need to do is we have to get a BIBC matrix formed as well as BCBV matrix formed for these systems. So, what we do actually, initially we remove the loop forming branches and then get BIBC matrix, and then we modify BIBC matrix such that we can include those loop forming branches. Like shown in this particular figure, we have seen that whenever actually, so suppose in this case this branch between 5 and 6, it is forming the loop. So, initially to get the BIBC matrix, we remove that branch and get the radial BIBC matrix. We have seen how to get that. So, we have seen that this column is corresponding to bus 2, this column corresponding 3, 4, 5 and 6, and we have seen that to get this 7th column of this BIBC matrix. So, this is your BIBC matrix, and to get this 7th column of BIBC matrix, since this branch is connected between 5 and 6, so you have to subtract column 6 from column 5. So, if you subtract this column 6 from column 5, you will get column 7. So, here subtraction will be 0 because 1 minus 1 0, 1 minus 1 0, here it will be 1, here it will be 1, and here it will be minus 1. And since last column is corresponding to branch current which is forming the loop, so here we are getting corresponding to I56, and we have seen that we have to put 1 here, and all other column we need to put 0. So, this is how we get BIBC matrix for weakly meshed system. Similarly, we have seen BCBV matrix also. So, as I told you, initially we have to get the BCBV matrix for radial system. So, here again this row is corresponding to 2, this is 3, 4, 5 and 6. In this case also, to get this 7th row, we need to subtract this row number 6 from row number 5. So, this is corresponding to this loop forming branches. So, here Z12 minus Z12 is 0, Z23 minus Z23 is 0, here we will get Z34, here I will get Z45, and here I will get Z minus Z36 because we are subtracting row 6 from row 5, and here we will get Z corresponding to loop forming branch, that is Z56, and the other entries in the other rows, they are 0. So, this is modified BCBV matrix including your loop forming branch, and once you get this, you multiply BIBC and BCBV. So, in one system I have taken, so for this particular system by taking the R and X parameters of different lengths of the line, and for that if you get BIBC matrix for this system, so this is BIBC matrix, and BCBV matrix by considering particular impedances of the line, you will be having this BCBV matrix. And then if you multiply, so I can say DLF dash, because this is not actual distribution load flow matrix, which is BCBV multiplied by BIBC, which you got earlier in this particular slide. You can multiply them, BCBV multiplied by BIBC, I will get this DLF dash. And then what we did, we divide this matrix in 4 parts, and then we have seen that this part of the matrix, which is basically radial part, we called matrix A, this part we called matrix B, this part we called C, matrix C, and this part we called matrix D. So, in this case modified DLF matrix, so actual DLF matrix we have seen that it is A minus B into D inverse C, but C is actually equal to B transpose. So, this will be equal to A minus B into D inverse B transpose. So, if you do that, this particular operation, that is A minus B into D inverse B transpose, you will get DLF matrix for this particular solution. And then we can go normal procedure which you have seen, or normal algorithm, step by step algorithm can be used for this case also. We already discussed it. Now today we are going to see another method, that is Gauss implicit Z matrix method. This method is based on superposition theorem. So, before going to the superposition theorem, suppose you are having this system here, again that same system of 6 buses I am taking it here, and then various currents are shown in this figure. So, if you see, if you model this system as a circuit, it will look like something like this. So, this is node number 1, and then impedance Z12, node number 2, this is this node number 3, then node number 4. So, this is 1, 2, 3, 4 and 5, and then there is one more branch from 3 which is going to impedance say 6. So, this is your 6 here, and then source is connected here. So, this is Vs angle 0 degree with source is connected. So, here this is Vs angle 0 degree source is available, and then we are having these loads I am modeling as a current sources into this network. So, these will be modeled as a current sources. So, this current will be say I2, then there is one current here, current source here which is I3, this current source here is I6, this current source here is I4, and this current source here is I5. So, all the sources, all the loads are modeled as current sources, and here we are going to apply superposition theorem. So, initially we will consider all the voltage sources in the network, and then we will consider all the current sources into the network. So, if you consider say in this case voltage source into the network, the circuit will be something like this. So, initially solve the voltages by considering only the voltage sources. So, in that case, if you consider only the voltage source, your network will be something like this. So, this is your 1, 2, 3, 4 and 5, and then we are having this voltage source here. Since we are considering only voltage source, and then next time we will consider current sources, and then we will calculate voltage at each of the node by both these methods and add it together. So, in this case, since we are considering only voltage sources, your network will look something like this, because current sources are considered as open circuit while we are doing the applying the superposition theorem. So, all the current sources will be replaced by infinite impedances. So, here there will not be connection with respect to ground. So, if we calculate voltages with respect to ground of each of this node, VNL2, no load voltage 2 will be in this case Vs angle 0 degree, VNL3 will be also equal to Vs angle 0 degree, VNL4 will also equal to Vs angle 0 degree, because there is no path available to ground. So, no current will flow. So, each of this terminal will get same voltage. So, VNL5 will be Vs angle 0 degree, and similarly VNL6 will be equal to Vs angle 0 degree. So, all the voltages, all the node voltages will be Vs angle 0, and I am calling VNL because it is no load voltage. We are not considering any loads here. All the current sources which are considered as a load, they are removed. So, only no load circuit is there, which is why V no load. So, this equivalently I can say VNL matrix, which forms VNL NL2, VNL3 up to VNL6, which is basically we are getting, so Vs angle 0 degree, Vs angle 0 degree, and all the entries are Vs angle 0 degree. So as we can say that this VNL will be available with us because this voltage is known during the load flow solution. Now as I told you, second step is to consider all the current sources and remove the voltage sources. So in that case your network will be something like this. So here I am removing this voltage source which is having negligible impedance, so it will be directly grounded. Then these are the impedances. And then there is one more impedance which is starting from here, Z36. So this is Z12, Z23, Z34, Z45 and Z36. And now we are considering all the current sources into earlier figure. So there is current source here, which is load current of bus 2. This is load current at bus 3. So this is I2, this is I3, this is I6 because it is node 6, this is 4, this is 5. So this is your I6. This current source is I4. This current source is I5. So now I want to solve this network to get the voltages at these nodes. Okay, so these voltages I can say V2 dash, V3 dash, V4 dash, V5 dash and V6 dash, that can be calculated by using say Y bus inverse multiplied by your current injected. So if you know the current injected and Y bus inverse, I can get the voltage sources. So basically we need to then get the Y bus of this. So in this case this is, let's say, your current injected. So current injected will be Y bus. So this is current injected at bus 2, current injected at bus 3, I injected at bus 4, at 5, 6, and this here will get multiplied with respect to this V2 dash, V3 dash, V4 dash, but I am calling this as actually delta V2 because this is voltage difference when we are considering load only. So here I am calling it as a delta V2, delta V3, delta V4, delta V5 and delta V6. So this multiplied by your Y bus will give me current injected. So this is nothing but here delta V2, delta V3, delta V4, delta V5, delta V6. These are nothing but node voltages when we are considering only the current sources. So delta V2 is voltage at bus 2. It is not difference. It is voltage at bus 2 when we are considering only current sources of the network. So in this case this will get multiplied with respect to this is voltage here. So this is your voltage, these are is current injected. So here this must be your Y bus matrix. So we can easily get Y bus matrix. We already studied how to form Y bus matrix. So for this particular network I can explicitly write. So if you consider this node number 2 here, so there are two impedances connected, admittances connected, those are Y12 plus Y23. And the impedance between 2 and 3, it is Y23. Then when we consider other entries will be 0 here. Then when we consider node 3, so there will be 3 admittances connected, Y23, Y34 and Y36. So for node 2 it is Y23 plus Y34 plus Y36. Then there will be between y23 is between 2 and 3. So here there will be minus y23, here it will be minus y34, and it will be minus y36 because it is between 3 and 6. Then if you consider node number 4, there are two impedances connected, two admittances connected. Those are y34 plus y45. So here between 3 and 4 this is y34, and between 4 and 5 this is y45. All other entries are 0. And then when consider node 5, only one admittance is connected, that is y45, and there will be between 4 and 5, so minus y44 will come here. And between 3 and 6 there is only one admittance, so y36 will come here, and there will be minus y36 here. All other entries are 0, and we can form Y bus matrix like this. So here the current injected, if you observe these current sources, they are in opposite direction of current injected. So these are nothing but minus I2, minus I3, minus I6, because current injected is in towards the node, and the direction of the load current which we are taking opposite. So whatever load current we are calculating, we need to take minus sign here. Now we have got this matrix, which is basically, if you see this matrix, it is, the structure of this matrix is something like this. I injected matrix, which is basically this part, is equal to your Y bus matrix, which is this. We know how to form the Y bus, and then this matrix I am calling delta V. Basically structure of this matrix is something like this. So I injected is equal to your Y bus matrix multiplied by your delta V. These are the voltages at this node which we are interested in. And then if you see, this Y bus can be splitted into two parts using LED decomposition. There are many methods. So I injected will be equal to, you were decomposing this into lower and upper triangular matrix multiplied by your delta V, and then this can be again written as, now here U multiplied by delta V, I am writing it as a matrix X. So matrix X, we know that it is U multiplied by your delta V. So since here if you observe this, it is low, we know that this L is lower triangular matrix, and I injected currents, they are known, because as I told you, these are actually just opposite of your negative sign of your load currents. So this matrix is known, so I injected at various buses is known. Then so by solving this we can get X, and it is easy because here this is now only lower triangular matrix. So in this case, if it is I injected at bus 2, I injected at bus 3, I injected at bus 4, I injected at bus 5, I injected at bus 6 will be equal to your lower triangular matrix. I am considering this matrix here. So lower triangular matrix will be L11, and then all entries will be 0 here, and then here L1, L21 into L2, so here, and then L31, L32, L33, 0, 0, 0, and up to L55 here, and this is getting multiplied with your X2, X3 up to Xn, which are unknown. I am starting from 2 because we are starting from bus number 2, that is why I am not taking X1 here, so it will start from X2. So in this case I can easily write your X2 will be equal to your I injected at bus number 2 divided by L11 matrix, this element of this matrix, and this is known because we have derive this LU matrices from Y bus only. So, L11 is already known, current injected is known, so X2 can be calculated. Similarly, your X3 can be calculated like this. So, it will be Li injected at bus number 3 minus L21 into X2 divided by your L22, and like this you can go on calculate up to Xn, or in this case it is X6. So, we can get up to X6 all the values, and once you get all the values of X, we can put this into this matrix. So, in this case this next matrix will be X2, X3 and up to X6, that will be equal to, and here this upper triangular matrix means U11, U12 and up to U16, U15 and up to U55, and these elements will be 0 here, all this. So, it is just upper triangular matrix. So, here also we can use same procedure to get this right hand side of this one, that is delta V2, delta V3 up to delta V6, and so you can use same scheme here. You can burst in vertical direction, that is first start from X6. So, X6 will be just you can say delta V6 will be equal to X6 divided by U55, and you can go on calculating till delta V2. So, this is how we can actually get all the voltages. Now, you have to apply superposition. So, here you have got, after doing this, you have got your delta V matrix, which is just by considering the current sources, and already you have got this VNL matrix, which is just by considering the voltage sources. So, this is due to current sources, which are basically loads, and this is due to applied voltage source. Okay. And if you add them together, I will get voltage which is applying the superposition. So, here we are applying superposition. So, we are going to add these two voltages, which is due to voltage source and due to load current. So, V will be equal to V no load plus delta V. Now, let us say what will be the steps of this algorithm. So, here say this is your generalized system, which is having n number of buses here. In this case, the step 1 will be, so here voltage at this node is known, so Vs angle 0 degree. So, step 1 like your all other algorithm. So, step 1 will be initializing initialization of bus voltages. So, we can initialize that, we can say Vj at 0th iteration will be equal to Vs angle 0 degree, and this is for j going from 2, 3 up to n, means all buses will be initialized with voltage Vs angle 0 degree in first step. In second step, construct your Y bus matrix. So, I can say construction and factorization, both we are doing factorization of Y bus matrix. So, once you get Y bus matrix, we can factorize, means we can say your Y bus matrix will be L multiplied by U, that is LU decomposition we are doing, factorization we are doing. Then step 3 will be initialization of iteration count. So, initialization of iteration count. So, iteration count k will be equal to 1 first, and then step 4 will be calculation of load current at each bus. So, load current will be calculated, we know that load current calculation. So, we know that current Ij at any kth iteration will be calculated by knowing the load at jth bus. So, PLJ plus JQLJ is load at jth bus divided by your voltage at jth bus, but which is obtained at k minus 1 iteration, and you have to take star of it, and this will be done for all j goes from 2, 3 up to n. So, all the load currents will be calculated, and then we know that your I injected matrix will be nothing but your matrix of minus I2 minus I3 up to minus In. So, from this I injected matrix also in this particular step. So, now I injected matrix is known, and so in step 5 we use that LU decomposition and get the delta V. So, calculate voltage due to load currents only, modeling as current sources. So, we have seen that I injected matrix is actually equal to your Y bus matrix, but we have seen that it is actually decomposed into two parts. So, that is actually equal to your L matrix multiplied by U matrix into your delta V. So, here we can get the delta V matrix, and then step 6 will be update the bus voltages by superposition. So, in this case superposition still will be applied. So, we know that V j or sorry here voltages of the buses at kth iteration. So, this is injected current. So, delta V we are calculating at kth iteration by considering injected current which is taken at kth iteration. So, all these are related to kth iteration. So, voltages of the buses at kth iteration will be equal to V and L. No load voltages, as I told you, they are not changing at all, they are remaining constant. So, V no load plus whatever delta V which you are getting it here at kth iteration. So, this delta V which is at kth iteration. Then step 7 will be comparing or calculating the error. So, error in the voltages. So, error in jth voltage in kth stage, kth iteration will be equal to voltage of jth bus at kth iteration which we are getting it here. So, this is one entry minus voltage of jth bus at k minus 1th iteration, and that will give us error in jth, and this step will be done for j is equal to 2, 3 up to n. So, we can get the error in all the bus voltages, and step 8 will be to calculate max error. So, in this case max error will be E max at kth iteration will be nothing but maximum of all the errors which you have calculated in earlier step. So, here we have calculated E2, E2, E3 up to En. So, it will be E2, E3 up to En which is we have calculated at kth iteration. So, that is why I am writing k here. So, we have got this maximum error, and we know that in step 9 we will compare this maximum error with tolerance, compare with tolerance. So, if E max at kth iteration, if it is less than or equal to epsilon which is basically tolerance value, then stop. If this condition is getting satisfied, then stop and print the results. So, we have got the results. Else update the iteration count that is k is equal to k plus 1 and go to step 4. So, here we have to go back and again calculate new currents, injected currents, then get the delta V by considering injected currents only, then update the voltages, again compare the voltages, keep this loop till the convergence happens. So, your Gauss implicit Z matrix method works like this. So, in today's lecture we have seen Gauss implicit Z bus matrix method, and initially we have seen the introduction of this, how we can get it. So, we have seen that we need to use it superposition theorem here. So, initially the no load voltages will be calculated removing all loads, and then in second step all the loads will be modeled as current sources and you will get your delta V. So, no load voltage plus delta V will give actual voltage, and we have to keep iterating till the convergence will happen. So, here we completed the load flow studies, and if you remember load flow studies, we have compared the algorithms of transmission systems, load flow algorithms and transmission systems, and load flow algorithm distribution system. So, we have seen that in case of transmission system we have used Gauss-Seidel method, Newton-Raphson method or fast decoupled method, and as explained there those methods can be used for distribution system with little modification. However, because of high R by X ratio, convergence of these methods is very slow, and other advantage of distribution system is they are radial one, and then we can because of this radial structure we can develop some simple and efficient algorithm for distribution system. So, that is why instead of going for traditional methods like Gauss-Seidel, Newton-Raphson, we have gone for other methods which are efficient for distribution system. And we have seen that those methods are basically backward forward sweep algorithm. We have seen it for balanced system first, and then we have used it for unbalanced system also, considering all the three phases together. Then we have gone for direct approach for load flow analysis, and we have seen that from the topology of your circuit or graph of your circuit, we can get BIBC matrix and BCBV matrix, which is basically consisting of impedances, and multiplication of this BCBV multiplied by BIBC, we have got distribution load flow matrix. And using this matrix we can get your update of voltages, and it is, you can say, for next step of backward forward algorithm. So, we have seen direct approach based load flow also. First we have seen it for radial systems, it is balanced as well unbalanced, and then we have gone for using it for weakly meshed system. So, we have seen one example also for radial as well as weakly meshed system. And then finally, we have seen Gauss implicit Z-bus matrix method today, which is again widely used for distribution load flows. So, here we will complete the load flow portion, and next class we will start with short circuit analysis. Thank you.